Yeah, so as I was saying, I will be should be done with the grading by tomorrow, maybe today. At least the first part of the exam I'll grade it today for sure. I'm almost halfway, have graded like half of it already. And then yeah, once I have the grades, I'll send you the solutions to the exam. Typically I make some sort of comment most of the time when I'm grading them, but if you have any questions about the exam grade, you can either email me or we can discuss it over office hours after I have posted them. Uh, so today, yeah, we're starting like a slightly new topic. So the first thing I have to tell you about is linear combinations of vectors, which we haven't really talked about before. And after we do that, we can talk about the determinant of a matrix. Um, Let me start with a system of equations. So when you look at a system of equations like this, there were two interpretations we were giving to this system of equations. So for example, the first interpretation is that for this particular case, so the first interpretation is that each equation here represents a line, right? Each of these would be like the equation of a line. Is the equation of a line, and so solving the system is asking where the lines intersect, whether the lines intersect or not. Um, then the second interpretation what was in terms of matrices, if you remember. So let me rewrite this as a matrix. So you, in terms of matrices, you have you can rewrite this as 1 minus 1, 3, 1, xy equals -1, 9. Right, so if you wanted one way to think about this system of equations, that you have the vector xy here, you have the matrix A here, um, and the idea is like the output, right? Remember the output, when you think of the matrix as a machine or a process, the output would be the product, so it would be -1, 9. So from this point of view, like solving the system of equations is kind of trying to find the right input that will give you the desired output. So solving the system means finding an input, finding the values of the input xy, which will give the output. Will give the output -1.9. So from this perspective, it's just like a kind of input-output type of thing where you're given certain output and you're trying to find the input. Okay. In this case, I don't know if you remember that the solution to this matrix was, I think this is a kind of like a system of equations we have been doing a lot of the time before. So the solution, I think I have it here. The input had to be 2, 3. So x had to be 2 and y had to be 3 in this case. The correct input was xy equals 2, 3. Okay, so far so good. Any questions about this up to this point? So again, we kind of already saw both of these points of view before. Now what I'm going to do next is kind of give you a third perspective of what's happening when you're trying to solve a system of equations, which is also a convenient perspective and will become more important as the course progresses. So the third interpretation is what is related to this thing called like a linear combination of vectors. So again, just going back to the system of equations, if you have x minus y equals -1 and 3x plus y equals 9, then one way to rewrite this in terms of vectors is just to write, we have typically written this already as a vector, so you can write this like as -1, 9. And then you just write each equation here as the entries as a vector. So you can write x minus y and 3x plus y. Okay, so that's not too surprising. It's just like remember an equality between vectors is an equality between their entries, and so this kind of makes sense. But what I'll do now is something slightly different, which is kind of to break this vector apart into two pieces. Let's stuff. I'll break this vector into a sum of two vectors, and how I will determine this is by putting like the stuff with the same variable on one vector, putting the stuff that has x on one vector, and putting the stuff that has y on one vector. So what I'm trying to say here, I'm going to write it this way. So what has x in this expression, 3x and 3x, and what has y in this expression, oops, what has y is negative y. So I'm just saying that if you look at the sum, I mean, if you remember how the sum of vectors works, the sum of these two vectors is the same as this vector, right? Because to add vectors, you just add the individual entries, right? So this one with this one gives you this, and this one with this one gives you that. Is that making sense? So far, so good. And this doesn't seem so obvious. I mean, it may not be too clear why you would do that. Is kind of may look a little bit dumb, but what you can do next, the advantage of breaking this vector into these two pieces is that since a variable, everything that involves a variable x is the first vector, you can kind of pull out the x from the vector. So this becomes x times the vector 1, 3. And then the other one becomes y times the vector minus 1, y, right? So that's why it's convenient to break it in terms of the same variables, because since now each vector has only stuff that depends on one of the variables, you can factorize the variable or take it out the vector. Right? So is this making sense how I got to this equation? So what I'm saying is that this system of equations, right, is secretly the same as this equation. Okay? But the advantage of seeing it this way is that here, what you're trying to do, so if you look at this equation, let me put it inside a box because it's kind of important. So if you're looking at this, if you look at this equation, what you're trying to do is kind of to express this vector as a sum of these two vectors. So from this perspective, we're trying to express the vector -1, 9 as a sum, as some sort of sum. Is that making sense? So just to give you, it's better to see this more visually. So let me give you like a better picture of what's happening. So let me go to GeoGebra for a second. Okay, so here, what do we see here? So we have the first vector, which was -1, 9. I don't know if you see me typing it. Oops, need to. Okay, there. That's where -1, 9 is. So there's this vector, which you see here. Let me leave that in black. Okay, so this would be that vector. I don't need its length. Okay, and then there was the vector 1, 3, right? So let me put 1, 3 here. I'll put it in red because that's the color that I was using on the um on the on the on the iPad. So let me change it into red. Okay. So this is that vector. Okay. And then there was this other vector -1, 1, right? Um, which is the blue one, right, on the iPad. So in a sense, what I'm saying is that the system of equations, one way to think about it, if you want to think, if you want, is that you are, oops, let me undo this. You are trying to express the black vector as a sum, of the blue and of the red and the blue vectors. But yeah, if you see it in this picture, right? In this picture, it's clear that, I mean, that is very unlikely. I mean, in this particular case, like that doesn't seem like something that would happen, right? So that's why if you look at the if you look at the equation, you are kind of allowed to multiply first the red and blue vectors by some factor. So you're allowed to rescale the vectors before trying to match them as a sum into the black vector. So what I'm trying to say is that let me introduce a slider. Sorry, it should have been. Okay, so let me see. Let me put it here. Perfect. So I'm going to delete this label here and put it. Okay. So what I'm going to try to do now is kind of instead of like I'm going to take the red vector, but I'm allowed to rescale it. Do you see like how I'm changing it? So like the arrow that you see kind of increasing in size right now is the one that you get if you start rescaling the red vector. So uh, okay, I need to change. Okay, stop the animation. So I'm not allowed to rescale this vector. And then I'm also allowed to rescale the blue vector. So you can introduce another slider to rescale the blue vector. Let's call that, I mean, U2, which is V times W. Okay, so this one will be blue. So I'm rescaling this vector. Okay, as you see here. And then what I'm asking is like, oh, now imagine that I kind of rescaling both at this, like I'm allowed to rescale the red one and the blue one by some amount. Okay. And so the question is, can you find like an appropriate rescaling of each vector so that when you add them together, you get the black one? So if you solve the system of equations, you remember that the system, the solutions were x equals 2 and y equals 3. So what I'm trying to say here is that if you take these two rescalings, like if you multiply the, I'm trying to get, oh, here it is, 3. So what I'm saying is that if you multiply the rect vector by a factor of 2, so you're making it twice as big, and you multiply the blue vector by a factor of 3, then the sum of these two will give you the black one. I mean, you can check it by doing the entries, or it's basically adding the vectors that are being called U1 and U2 on the algebra. But I mean, pictorially, what's happening here is like you're kind of, you know, you are just trying to match the vector to like a rescaled version of the original two vectors. Is that making sense? So that's kind of the meaning of the linear combination in this particular problem. So let me just make a picture of that on the tablet. So what I'm trying to say is that you had here the vector xy, you had this vector negative 1, 9, right? So here you had negative 1, 9. You had this vector 1, 3, and this one doesn't quite work. So you rescale it, right? You rescale it by a factor of 2. So you rescale it until you get to 2, 6, which is 2, 1, 3. Okay. And then you had this other vector, which was negative 1, 1. And again, you have to rescale it first. So let me rescale it to get to negative 3, 3. Okay. So, and then if you, right, if you add these new rescale vectors, you get -3 plus 2, which is -1. Oh, sorry. So yeah. And then 3 plus 6, which is 9. So I'm saying that these rescale versions, so that these two rescale versions do add up to -1, 9. So the rescale versions, is that making sense? Are there any questions about this so far? And that's what you call a linear combination of the vectors. So a linear combination of the vectors is basically like in this case, we were starting with two vectors. So you take the two vectors, you are allowed to rescale each of them separately. So you can rescale them first, and then you add them together, and that will produce a third vector, and that's called like a linear combination. So you say that a linear combination of two vectors, C1 and C2, you'll see why I'm calling them C1 and C2 in a moment, is um, is any vector that can be written as, so in this example, in our example, V equals -1, 9 is a linear combination of C1 equals 1, 3, and C2 equals -1. Is that making sense? So that's what a linear combination of two vectors looks like. Okay, and then let's see. This one is not so nice. And like a linear combination of three vectors kind of, for example, would occur using the same idea. So what's like a linear combination of three vectors? Let me see if I can show you that. So what would be like a linear combination of three vectors? It is harder to draw, but I'll try to make like some sort of like picture here. Well, in fact, I'll save the picture for later. So I mean, once you have three vectors, let's say C1, let's call them C1, C2, C3. Okay. Is any vector B that can be written as so again, what this means is like you take three vectors, you're allowed to multiply each of these vectors by its own constant. So you are allowed to rescale them, and then once you do that, then you can add them together, and you can get like the linear combinations in that way. Okay, so let me see if I can do this here. Okay. Yeah, I think I can. Let's see if I can show you this one here. So I'm actually going to define that in a second. So that's a good question, but actually I'm going to define that in a minute. So just to show you, I'm just trying to show you what it would look like in the case of three vectors. Let's see if I'm just trying to, okay. So let me try to rotate this here. I'm just trying to first enter it on GeoGebra, so okay, just give me a second. Okay. Aha. Okay. So yeah, let me go back to GeoGebra to show you how this looks like. So, okay, the picture won't look that great, but it will give you like the idea. So before, let me hide this one. I just want to take like a 3D perspective of what's going on. So before I had like these two vectors, like the blue, the red one and the blue one, right? And I was combining them into producing the black one, right? Then you could add like a third vector, for example, if you wanted, which is this red vector that you see here. Obviously, I wanted to use a different color. Is that for some reason GeoGebra is not allowing me right now? But just ignore the colors for now. Now you have this vector, and that vector. And then you could now you can use the three to combine them, right, into a new vector. So you could, I mean, again, you're allowed to multiply or rescale them if you want, but then you can just take a new vector, which is like, let me see if I can put it here. So I'm going to do u1 plus u2 plus c. Okay, so you are allowed to combine them, and you'll get a new vector, which is in the sum, but it is kind of not looking too great. So let's see. Oh, okay. You could put like, let me put it like -1. Okay, right. If you combine these vectors here, here. No, this is fixed. Okay. Again, it's the color is kind of ugly, but just ignore that for a bit. So you can combine the two vectors on the plane with this third vector, and you produce a new vector. Okay, so you would say that this one, that one that is ending at G, is like a linear combination of these three vectors. Okay, so again, like the point of a linear combination is just to think that you started with some vectors, and you kind of are allowed to rescale them, take their sum, and then produce a new vector. Okay, so just to make a picture of the situation, like you had like in this example, you had like these three vectors, like maybe C1, C2, and C3, and you're allowed to rescale them first, and then when you add them together, you get something here, which is a sum of these three, which is what we're calling xc1 plus yc2 plus cc3. Okay, so again, like the way to think about linear combinations is just like interesting sum. So that's kind of, as you can imagine, like when you have more, if you have more vectors, it is kind of like the same idea. So when you have n like let's call it p vectors, um, or no, let's call it n vectors. Yeah, p is a linear combination of them. If you can express b as a sum of the vectors, okay? Meaning that b is like as a, let me say, rescaled sum. The thing is, like once you have more vectors, like again, you kind of run out of names. So instead of like using the letters x, y, z, you or x, y, z, w, which you can, like when they're for variables, that's kind of for vectors, that's good enough. But when there are many, it is just better to call them x1, x2, x3, x4, and so on. Okay, so just to give you an example to make it a little bit more concrete, here's an example. is a vector B 3, 4, 5, a linear combination. Okay, so what I'm asking here, so the question is whether um, B, um, the question is like, if you take C1 and C2 and C3 and C4, is there a way to combine them, right, to add them together so that you get B? Right, so it is asking whether this equation can be solved. So can the equation be solved? And well, since this is like 4 variables, that means, sorry, I should have put this like without the without the without the arrow. You can, since they're like, we're talking about 4 vectors, if you want, you can call them x, y, z, w to just make it more natural. So what is xc1? Xc1 is x, x2, x. What is yc2? Yc2 is minus y, y, minus y. What is z, c3 is 0 to z, z. And what is wc4 is w, 0, 3, w. And what is b? B is 3, 4, 5. Is that making sense? So that's actually what, when you multiply each vector by a fact, by the variable, that's what each vector becomes, right? I'm just putting back the variable inside each entry. So actually, the reason why I'm doing that is that secretly, if you add these vectors together, this gives you the first entry x minus y plus w, then x plus y plus 2z, and then 2x minus y plus c plus 3w equals 3, 4, 5, right? And that's a system of equations. I mean, I kind of like, it looks like I'm going in circles, but I'm just trying to show you explicitly how this looks like. So it gives you like this system of equations. So what I'm trying to say is that you should always think of as determining whether a vector is a linear combination of others is always about solving a system of equations. So that's like the what I'm trying to, like the first takeaway of what I'm doing right now. So determining whether a vector is a linear combination of others is about solving a system of equations. Is equivalent to solving a system of equations. Is that making sense? So that's what I'm trying to do here. And just to, what if you wanted to write this in matrix notation, what is that system of equation equal to? It's 1 minus 1 0, 1, 1, 1, 2, 0, 2 minus 1, 1, 3 times x, y, z equals 3, 4, 5. So can anyone notice something interesting about these columns or about this matrix? What are the matrix? What can you notice about the columns of this matrix in terms of the vectors that we had in our original problem? What can you say? How are these columns related to the original vectors? They are just the vectors we started with, right? The first column is 1, 1, 2, and that's the vector 1, 1, 2 here. The second column is negative 1, 1, 1, which is the second vector here. The third column is 0, 2, 1, which is what you see here. And the fourth column is 1, 0, 3. So that's why I was calling the vector C1, C2, C3, C4, because the C stands here for columns. So these are literally the same vectors that we started with. So essentially that gives you like the method to determine if something is a linear combination or not. You just set up a system of equations where the columns of the matrix are the vectors that you care about. So, and that's just kind of like the most important thing of what I have said thus far. So let me just write it as a procedure for determining if the vector B is a linear combination C1, C2, C3, up to Cn. You form a matrix whose columns are these vectors. So it's only two things that you have to do. Form a matrix A whose columns are C1, C2, up to Cn. Sometimes you can write that pictorially this way, although you have to be careful because again, like each of these is a vector. So this is kind of saying column 1 is here, column 2 is here, column n is here. So you form that matrix and you consider the system AX equals B. So consider the system of equations AX equals B. If the system has a solution, then the B is a linear combination. So if the system has at least one solution, because remember a system is either 0, 1, or infinite solutions. So at least we require one solution. If the system has at least one solution, B is a linear combination of the vectors. Otherwise, it is not. If there are no solutions to the system of equations, it is not. Is that making sense? So all that I have said so far is kind of saying that this stuff about system of equations is, I mean, linear combinations. At the end of the day, the way in which you use to solve them is by like setting up a system of equations and like figuring out whether you can solve that system or not. So we are, in terms of techniques, it's not that we're learning anything new. It's just that we're interpreting what it means to solve a system of equations. So from this interpretation, solving a system of equations is the same as figuring out whether the vector B is a linear combination of the columns. So it's just like another perspective of what it means to solve a system of equations. Is that making sense? So now I can just to for now we don't need to know too much about this because like essentially it is the same as finding systems solving systems of equations. So there's not really too much new. What's a little bit useful in a couple of minutes or maybe tomorrow once we talk a bit more about the determinant is this concept of linearly independent. So before I give you that, um, let me just ask like more of a conceptual question, so just to make sure whether this is making sense or not. So remember that the zero vector is like the vector whose entries are all zero, right, etc. So the zero vector always has zeros, right? So this is the zero vector. So the question is a zero vector a linear combination of any given set of vectors? So is the zero vector a linear combination of some of any vectors? So I don't know if the question is making sense. I'm giving you like some vectors, C1, C2, up to Cn. You don't know what they are. They are completely arbitrary, right? So I'm just asking, is a zero vector going to be a combination of these? Yes or no, right? So what do you think the answer is going to be? Like, oh, I'm asking whether you can always make it a linear combination of them. So right, like in other words, I'm asking whether you can take a sum of these vectors, right? Well, I rescaled some of the vectors, right? And produce the vector zero, right? So is there a way to produce the vector zero by rescaling the vectors appropriately? Yes or no? And you don't know anything about these vectors C1 up to Cn. So if there's like a way to do it, it should be like a very simple way to do it. So remember that this is the same because of what I just said. This equation, figuring this out, is the same as trying to solve this system of equations, right? But now what happens? What was the name that we gave to this system of equations when the zero was appearing on the right hand side? It was a homogeneous system, perfect. So this was so figuring out whether zero is a linear combination is the same as studying the homogeneous system, right? So this is a homogeneous system. And what did we say about the solutions of a homogeneous system? What happened with homogeneous systems of equations in terms of solutions, right? Again, in general, there are three possibilities for a system of equations: zero solutions, one solution, or infinite solutions, right? But in the homogeneous case, there's always at least one solution, right? The homogeneous system always has at least one solution, so can always be solved. Right, you just have to take like x1 equals x2 equals x3, blah, 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 equals xn equals 0. Right, so the solution to a homogeneous system of equations can always be found by setting um, each variable equal to 0. Is that making sense? But so we say, if that's the only way to solve the system, okay, if that's the only way to solve the system of equations, then we say that the vectors are linearly independent. Okay, so we say that C1, sorry, yeah, the C1, C2, C3 up to Cn are linearly independent if AX equals 0 only has a trivial solution, where A, again, is a matrix whose columns are these vectors. And so the other case that can happen is that the system had infinitely many solutions, in which case you say that they're linearly dependent. So, and therefore, when AX equals 0 has infinitely many solutions, the vectors are called linearly dependent. Is that making sense? So figuring out like the linear independence or dependence of vectors is just asking whether the zero vector can be written in more than one way in terms of those vectors as a linear combination. Is that making sense? I'm going to do an example first to kind of show what that means like more geometrically. Like it's good to have like at least some examples in the plane in 3 dimensions to see this more clearly. So, but let me, before doing those examples, let me check first if there are any questions up to this point. So just to give you an example, let's do two vectors in the in the xy plane. So let's try to answer this question. When are two vectors? So you have two vectors on the xy plane. Let's call them C1 and C2 as before. So I'm going to call C1 here and C2. Let's put it here. So my question is, when are the vectors? Let's say you have two non-zero vectors, C1 and C2. When are these vectors linearly independent? So again, to figure out the linear independence or independence of the vectors, what you have to look at is at the homogeneous system. Okay. So what happens? What happens if this is? What happens if the vectors are linear? It's easier to answer like the question if the vectors are linearly dependent. So what happens if C1 and C2 are linearly dependent? If C1 and C2 are linearly dependent, what does that mean? It means that this equation can be solved with solutions that are not just x equals 0 and y equals 0, right? Then let's call this equation star. Then star can be solved. Star has solutions uh, which are not just x equals 0, y equals 0. Is that making sense? That's what linearly dependence means. It means that there are more solutions than the silly one. Okay, so linearly dependent means that there are more solutions to the homogeneous system than just putting every variable equal to 0. Okay, so at least one of these two has to be non-zero, right? So say for example, let's say that that y is non-zero. Okay, so we can go back to this equation, which I'm right. Another way to write is like in this way. And since y is non-zero, you can solve for C2, right? And so what does this equation say? It says that C2 has to be what in terms of C1? It's C1 times a number. So what does that mean? What happens if one vector is a multiple of the other vector of another vector? So like if one vector is a multiple of another one, it kind of means that they're parallel, right? Or anti-parallel. I mean, whether you want to use the word anti-parallel, because if the coefficient is negative, it's more up to you. But it's more the important thing is that this is saying that C2 is a multiple of C1. So in other words, like you have the vector uh, C1, and then you have this line. So that this is saying is that the vector C2 is on the same line as C1. I mean, again, it could be pointing maybe in the same direction or in opposite directions, but it belongs to the same line that passes through C1. So C1, C2 are parallel, or I mean, again, it could be parallel or anti-parallel. Or in other words, they belong to the same line. Is that making sense? So linearly depend, and this is a two linearly dependent vectors, on the plane. So two linearly dependent vectors of the plane literally belong to some given. They can both be drawn on the same line. So in the linearly independent case is when that doesn't happen, so the vectors are non-parallel. Is that making sense? So in the linearly, again, independent, they're both on different lines, right? So they're on different lines. So what does that mean? It means that uh, if you draw, what's another more elegant way of saying that they're on different lines? What that means is that you can draw a parallelogram um, whose sides are these two vectors, right? Everyone sees a parallelogram here. And so saying that they're linearly independent is the same as saying that the vectors, this parallelogram has a non-zero area. Area of the parallelogram formed by C1, C2 is non-zero. Is that making sense? But this area of the parallelogram is what I'm about to, in 5 or 10 minutes, call the determinant of the two vectors. So this area is basically going to be called what's called known as a determinant. And so what that's going to say is like in the linearly independent case, the two vectors are linearly independent if they have non-zero determinant. So I'll make that more precise in a couple of minutes, but I'm just trying to lay it out there, like to say that in the case of two vectors on the plane, like the linearly independence is really very easy to study because it's literally just about the area of a parallelogram. Okay, so yeah, are there any questions about this? For now, I mean, again, like this thing about the determinant, you don't have to worry too much about it. I'm going to tell you all about it in a couple of minutes. So I just want to make sure like that this is clear. Like, so linearly dependent is parallel vectors or vectors on the same line. So it's kind of squashing the parallelogram, right? The thing is, like, if you try to make a parallelogram with these two vectors, like you kind of collapsed it to a line. So it has like zero area. And in the linearly independent case, since they're not both on the same line, there's like some sort of like some size, some area to it. And so you can say this condition in terms of that area. Okay, so what I'll do, so what I'm going to do next is kind of start talking about this determinant business. First in the 2x2 case, because everything can be made super explicit there, so it's kind of convenient because of that. But it's just because it's slightly different topic. Let's take a 5-minute break, and when we come back, I'll start telling you all that you need to know about the determinant. Okay, so as I was saying, now I'm going to tell you about the determinant, which is a very useful thing about a matrix, a very useful piece of information about a matrix. But we'll start first, like slowly on the 2x2 case, because once you understand the 2x2 case well, then a lot of many other properties are very easy to prove. So let me talk to you about the determinant of a 2x2 matrix. So again, I'll think of the matrix is 2x2. So I'm just going to call the I'm going to write the matrix in as usually I would have written before I wrote things as A, B, C, D. I mean, it doesn't matter which one is called B and which one C. The only reason why I'm doing it now this way is that this way, if you do it this way, you can think about it of the first column as a vector and the second column as a vector, right? So it's kind of just useful because of that. So let me call them column 1 and column 2. Okay. So there's like a nice, like there are a few ways to think about it, but this is like a very nice perspective. So here's like interpretation 1 of what this determinant is going to be. So you can start on the xy plane with what's the unit square. So let's begin with the unit square. I need a different color. Okay, so since this is a unit square, this is a vector. On the unit square, what's the entry of the unit square? This is like 1, 0, right? But I'm going to write it as a column for now. So this is a vector 1, 0, and this is a vector 0, 1, right? These two vectors are so special that, or so basic that they get their own name. So in a physics class, it's typically what you call I and J, if you have seen those. But just in linear algebra, it's more convenient to call them E1 and E2. So I'm going to call them E1 and E2. So the E1 just has like a 1 in the, E1 has a one in the first entry, and E2 has a one in the second entry. That's kind of the notation. Is that okay? So the unit square, you can think about the unit square as the square that you get by, you know, making a parallelogram from the vectors E1 and E2. Okay, so your unit square is a parallelogram formed from E1 and E2. Is that okay, everyone? So far, so good. Is that making sense to this point? So again, we can start with the unit square, and we can identify very easily the size of the unit square. Now here comes the next step, which is, well, once you have a matrix, right? We have this matrix which I'm calling A, B, C, D, right? Remember, a matrix is something that you can use to multiply a vector, right? Like a matrix is supposed to, it's kind of like a tool to transform a vector, right? So you can consider multiplying the matrix A by the vector E1, right? Or you could also multiply the matrix A by the vector E2, right? So let me just, I will write this very explicitly. So it's A, B, C, D by 1, 0. And A, B, C, D by 0, 1. Okay. So can anyone tell me what do you get if you do those two products? So what do you get if you do the first multiplication? What is the answer for this? Well, it's just a vector AB, right? So if you do this multiplication, this is just AB. But what is AB? That's just the first column, right? And if you do, that's just the first column of the matrix. And if you do this second multiplication, you get CD. And this is just C2. So what I'm trying to say, okay, let me redo the picture again. So what I'm trying to say is that if you have the unit vectors E1 and E2, you can produce a unit square, right? You have the unit square. And then if you multiply each vector by the matrix A, if you multiply each vector by the matrix A, then you get two new vectors, right? The E1 becomes A E1, which is the first column of the matrix, and E2 becomes A E2, which is the second column of the matrix. So what I'm saying is that the matrix multiplication turned the square into a more general parallelogram, right? So that's one way to think about what the matrix multiplication is doing. So now you get a new, you may not even get a square now, because the angles may change. So the matrix multiplication, what it's doing is, so the matrix multiplication transformed the square, the unit square, into a parallelogram. Is that making sense? Just give me a second. Is that okay? So again, from this perspective, multiplication, what it does is turn the square, the matrix turns the square into a parallelogram, and the area of this parallelogram will be called the determinant of A. Okay, so the area that, because what's the area of the unit square? So the area of the unit square is area 1. Once you turn this unit square into something like this, like you may not know. I mean, you like the area may not be 1 anymore, so the area just gets called the determinant. So the determinant, so the determinant of A, which is called det of A, that's usually the name that's given to the determinant. And there's another notation that puts like absolute values, um, like an absolute value notation for the determinant, but I find it more confusing. So I'll just always write it in terms of that A is the area of the parallelogram formed by the columns of the matrix, whose sides are the columns of the matrix. Is that making sense? Any questions up to this point? So, okay. So let me just, the thing is that you have to be a little bit more careful because there are actually a couple of possibilities. So it ends up being useful to give the, like a sign to the areas or to the determinant. So it ends up being convenient to allow the determinant to be positive, or negative. But it is convenient, but actually it can be allowed to be negative. So, oh, is that, let me put here like signed area. So signed area just means that it is the area with the sign. So it's like an area with a which could be positive or negative. So it can be allowed to have a sign. So I'm going to explain where this plus or minus comes from. Okay, so the thing that actually happens is that there are three possibilities. So let me explain what's going on here. So here's option 1. So in option one, you start with the unit square. So in option one, you start with the unit square, and what happens is that it became a parallelogram using the matrix A, right? So use the matrix A to turn it into a parallelogram. Okay. And the the thing here is that in this case, you can rotate, like in this situation, like you can rotate the vector C1 counterclockwise to get to C2. So let me put it this way. Using an angle less than 90 degrees. Sorry, then 180 degrees. Okay, so like the only thing that I'm trying to say is that in this case, like you can look at C1, and if you rotate it counterclockwise by less than 180, then and get to C2, then in this case, like the determinant is just the area of the parallelogram as a positive number. So in this case, the determinant of A is going to be positive, a positive number, and it's just the area of the parallelogram. Okay. So when a counterclockwise rotation is needed, the determinant you consider it positive. Basically, that's what I'm trying to say. So let me pause here to see if there are any questions. So here's like option two. This is what the second thing that could happen. Oops. So the second thing that could happen is that you have let me put it like this. Now E1, when you do the matrix multiplication, E1 now is kind of aligned here. And then E2 ends up being here, goes here. So the parallelogram now looks like this. Okay, and so if you look at the situation, right? What's happening here? What happens here is that if you wanted to rotate, right? If you wanted to rotate the pink vector into the blue vector counterclockwise, you would need more than 180 degrees, right? So it's better to think about it that you are instead going to rotate this vector into this vector clockwise using an angle of less than 180. Okay, so in this situation, what happens is that you can rotate C1 clockwise, and now put a emphasize that to align it less than 180 degrees. Is that making sense? So are you saying that in one situation you would need more than an angle less than 180 clockwise, or more than 180 counterclockwise? Sorry, or more than 180 clockwise, and in the other situation you need let me say it again. In one situation you need one angle less than 180 counterclockwise, and in the other situation you need an angle less than 180 clockwise. So it's just like what changes is that one is counterclockwise and the other is clockwise. So in this case, when the angle is clockwise, the determinant is going to be minus the area of the parallelogram. So in this case, the determinant of A is going to be negative, a negative number, and it's minus the area of the parallelogram. So the minus sign is just there to indicate whether the rotation was clockwise or counterclockwise. So the point of the sign of the determinant is telling you whether you needed a counterclockwise or clockwise rotation. So the sign of the determinant indicates whether a counterclockwise or clockwise rotation was needed. Okay, is that making sense? So it is like just keeping track of the what's sometimes called the orientation, like how you have to orient the vectors to get from one to the other. And then finally, option 3, what could happen? Like, okay, in option 1, the angle needed was counterclockwise. In option 2, the angle needed was clockwise. And in option 3, what happens is that the vectors kind of collapse. So in option 3, let me draw the picture again. In option 3, what happens is that after you do the matrix multiplication, after you do the matrix multiplication, the two vectors become belong to the same line. So in this case, what happens is that there's no parallelogram, right? So here, the parallelogram collapses into a line. So there's no area. So the area is 0. And so we define the determinant of the matrix as 0 in this case. It's taken to be 0. So the determinant of A equals 0 when C1 and C2 are on the same line. Is that making sense? But I don't know if you remember before the break, when was I saying that two vectors belong to the same line? When does that happen? When are two vectors on the same line? When did we have that before a couple of minutes ago? When the vectors were linearly dependent. So what this is saying is that determinant of A equals 0 when the vectors, when the column vectors of the matrix are linearly dependent. So, and this is like an important thing. Determinant of A equals 0 if the columns are linearly dependent, or another way to say it is if the columns are parallel, right? Otherwise, the determinant will be non-zero. Otherwise, the determinant will be non-zero. Okay, so this is already enough to do some examples. So for example, what is the determinant of 1, 2, 3, 6? What is its determinant? What would you say? You have to check whether, like, I mean, I'm putting it right after this property. So you have to look at the columns and you have to check whether the columns seem parallel or not, right? So are the columns parallel vectors, yes or no? So this determinant is 0 just because because the second column is 3 times the first one, right? So they're parallel or linearly dependent. But on the other hand, right, what's going to happen with the determinant of, for example, these? Here's another example. What is going to happen with this determinant? What if I change just this number to 0? Now, this one we'll see is not, this one is not going to be 0, and we'll see next time what the number should be. This is not 0, since, since the vectors are not parallel, right? Like there's no way to multiply this vector by a number to get to this vector or vice versa. I mean, it's very easy to see if you literally draw them. Like C1 is essentially on the x-axis, right? Here's C1, and here's here's C1, right? 1, 0, and here's C2. C2 is way bigger than C1, right? So, so yeah, they're not on the same line. So there is some sort of area here, right? There's some non-zero parallelogram, and we'll see that. We'll see next time what the formula is. Okay, in fact, like maybe just to finish for today, what I more or less will start doing next time is giving you like the formula for the determinant. So next time, what I will show you is that if you have a parallelogram, right, and one side is like AB, and the other side is CD, right? So you have these two sides. Oops. Then what I will show you is that the determinant, like the area up to a sign, the determinant of AB CD is going to be A times D minus B times C. So it's going to be this times this minus this times this. So I'll show you next time why that formula is true. It's not obvious at the moment, but that ends up being the formula. And so once you have that formula, then you can, yeah, you can start computing the determinants of a lot of matrices. But that proof is it's not too bad, but it does take a couple of minutes. So I'll tell you next time. But once you have those these formulas, so for example, in the one that I just wrote, 1036 is 1 times 6 minus 0 times 3, so that would be 6. So that's saying that the determinant in the area of of this parallelogram that you have here will have area equals to 6 meters square or square feet or whatever. Okay, so again, I'll show you that next time. So next time what I'll do is finish telling you some properties of the determinant of 2 by 2 matrices, do some examples with them, and then start telling you what happens in the general case, like 3 by 3 matrices, 4 by 4 matrices, 5 by 5, etc. Okay, but yeah, I think this is a good place to end. I'll see you tomorrow.